In this video, we're going to talk about the ratio test. This is based on the OpenStax Calculus Series, Volume 2, Section 5.6. The ratio test is one of the most important tests for determining whether or not an infinite series has a finite sum. In other words, is it convergent? It can also determine if it is divergent. In your textbook, it uses absolute values around the ratio, but in fact, the ratio test can be used if the series is based on a sequence with positive terms. In that case, the absolute values are not necessary. We are looking, in this case, at sequences where the series consists of non-zero terms. If the series was nothing but zeros, then adding up the zeros would not be a problem. Let's read the definition of the ratio test, which appears on the screen in front of you in the blue box. Suppose we have a series from 1 to infinity of a sub n, which is a series consisting of non-zero terms. Again, the series does not have to start at 1. It could start at 0 or 5 or 42. We typically use whole numbers, generally starting at 0 or 1, but that is not required. Now suppose that we let rho be the limit as n approaches infinity of the absolute value of the ratio of the n plus first term of the sequence divided by the nth term of the sequence. The letter there that looks like an italicized P is in fact the Greek letter rho, spelled R-H-O. It does represent the letter R in the Greek language. If the value of rho is greater than or equal to 0, but less than 1, then we know that the infinite series converges absolutely, which means that the absolute value of it definitely converges, as does the value of it without the absolute values. If the value of rho is greater than 1 or infinity, then we know that the infinite series diverges. If rho equals 1, then the test failed to work. We say that it is inconclusive and we must use a different test, such as the integral test or one of the other tests we've learned previously. Again, if the value of rho is 0 or less than 1, it definitely converges absolutely. If it's greater than 1 or goes to infinity, it definitely diverges. If the value of rho is 1, we have no idea, it's inconclusive, we must use a different test. Let's take a look at some examples of how to apply the ratio test. In example 1, we have the infinite series from 1 to infinity of 4 to the nth power divided by n squared. In this case, we are trying to determine whether or not this series converges. That is, does the infinite sum have a finite value, or is it divergent? We can use the ratio test. In this particular series, 4 raised to any power will be strictly positive, and anything squared is also positive, so that we know that these terms are all positive. In this case, it's not necessary to use the absolute values, but it is not wrong if you do so. We're going to let rho be the ratio of the n plus first term of the limit of the sequence divided by the nth term of the sequence, taking the limit from n to infinity. Let's write that down now. Rho will be equal to, and again, notice that you start at the bottom of what looks like the P and go around the ball at the top, and that is the Greek letter rho. This is going to be the limit as n goes to infinity. And again, you can write the absolute value, but they're not strictly necessary. This is the n plus first term of the sequence divided by the nth term of the sequence. In our case, when we replace the subscript n with n plus 1, we can write 4 the n plus 1 divided by, in parentheses, n plus 1 quantity squared, all divided by, now we need to represent the nth term of the sequence with 4 to the n divided by n squared. You'll note that when you use the ratio test, you frequently will get complex fractions, fractions within fractions. This is quite normal. Just remember that the top of the top and the bottom of the bottom both end up on the top or in the numerator. The bottom of the top and the top of the bottom both end up in the denominator. Let's do the algebra and simplify this now. And again, I was able to drop the absolute value because I know that these are strictly positive. It is never wrong to leave the absolute values in. In this case, this will lead to the limit as n goes to infinity of 4 to the n plus 1 divided by n plus 1 quantity squared times multiplying by the reciprocal of the denominator, n squared over 4 to the n. Now we have to do a little bit of tricky algebra here, which you need to recall that when you have 4 to the n plus 1 power, you can rewrite that in terms of 4 times 4 to the n. So 4 to the n plus 1 can be rewritten in this form, because when the bases are the same, you add the powers. 1 plus n is n plus 1. There is no way that we can cancel the n plus 1 quantity squared with the n squared, because the base of this one is n plus 1 and the base of this is n. However, by pulling one of the 4's off of 4 to the n plus 1, we now have two common factors, 4 to the n in the numerator, 4 to the n in the denominator, and they do cancel. Once we cancel those out, we will need to evaluate the rest. What is helpful at this point is to rewrite it so that we have the square outside all of the things being squared. This means that we can write the 4, which could come completely outside the limit if we want, times the quantity n divided by n plus 1 quantity squared. If we pull the 4 to the outside of the limit, this will lead to 4 times the limit as n goes to infinity of n over n plus 1 quantity squared. Remember that limits allow you to go inside the power, which means I can actually put the power after I do the limit. This will allow me to take the limit inside the second power and find the limit of n divided by n plus 1 and then square it. I could apply L'Hopital's rule since this leads to the form of infinity over infinity, but if you also remember the Bill Gates rule, this means that the ratio of the leading coefficients will be the value of the limit, in this case, 1. Applying L'Hopital's rule will lead to 1 over 1, which is also 1. This gives me 4 times 1 squared, which is, of course, 4. That's the value of the limit. Now we need to evaluate what this means in terms of the ratio test. Let's go back and review the rules for the ratio test. Similar to the p-series, the number 1 is the boundary between convergent and divergent things. Unlike p-series, however, they're in the opposite direction. For a p-series, if p is 1 or less, then it diverges, but if p is greater than 1, it converges. The ratio test is the opposite relationship. On the ratio test, if p is 1, we know nothing. It's an inconclusive test and we need to do something else. But if p is less than 1, it is convergent, not divergent like a p-series. If p is greater than 1 but still finite, or if p gave us infinity, then we know that it is divergent. Going back to the example, we got 4. Because 4 is greater than 1, that means that this one is definitely divergent. Let's take a look at another example. On this particular example, we have the infinite series from n equals 0 to infinity of n times 1/2 to the nth power. The 1/2 to the nth power is similar to a geometric series, but geometric series are not multiplied by the index n. Before we start, we need to make sure that the divergence test is satisfied, or rather that it is inconclusive. In other words, if the limit of this sequence does not go to 0, I know there's no way this will be a finite sum. So first I should check and make sure that the divergence test is inconclusive. That is our first step. Let's take a look at it now. Check the divergence test. The divergence test is the one that says if the limit as n goes to infinity of a sub n is not 0, then it diverges. We need to check this limit and make sure it's going to 0. We're going to be evaluating the limit as n goes to infinity of n times 1/2 to the n. The first thing we would always do, of course, is just plug in. In this case, when we plug in, we have infinity times 1/2 to the infinity power. It's hard to tell what this is going to come out to be. However, if you split up the 1/2 to the nth power and think of it instead as n times 1 over 2 to the n, remembering that 1 to any finite power is still 1, you will realize that the n is going to give you an infinity as the limit approaches infinity, but 1 over 2 to the n will approach 0. This means you have infinity times 0, which, as you know, is one of the arithmetic indeterminate forms. We need to be able to apply L'Hopital's rule, so before we can do that, we have to convert this into one of the two basic forms. 0 divided by 0, or infinity divided by infinity. I could move the n, or I could move the 1/2 to the nth power, or in this case, the 2 to the nth power. Because I used this form here to analyze and see what was happening to the limit, it makes more sense to go ahead and rewrite the limit in that form. This means that the n is going to slide to the numerator, and the 2 to the n slides to the denominator. In fact, this will generate exactly the same sequence of numbers that the original did. In this case, now when we plug in infinity in place of our index n, we have the form of infinity divided by 2 to the infinity, but 2 to the infinity is infinity, so we have infinity divided by infinity. This is also an indeterminate form, but it is one of the two basics, and that means that we can now apply L'Hopital's rule. If we apply L'Hopital's rule to this, we will see that we get the next expression. Remember that in order to apply L'Hopital's rule, you must have one of the two basics, and your numerator function and denominator function must be differentiable as you approach the limit value. N is a line which is differentiable everywhere. 2 to the n is exponential, which is also differentiable everywhere. So I am allowed to apply L'Hopital's rule. This leads to the limit as n approaches infinity of 1 divided by, well, the derivative of an exponential is the exponential. But since the base is not e, I have to include a constant, which represents the natural log of the base, or the natural log of 2. The natural log of 2 is a constant which could be pulled outside. At this point, I would plug in again. When I plug in infinity in place of the n, I can see that this is going to drive the limit down to 0. This means that the divergence test is inconclusive. In other words, it does not necessarily diverge. I can't tell. Now I'm going to apply the ratio test. When I apply the ratio test, I can apply it either to the original form or to my revised form. I generally find it easier to use the revised form. Now I'm going to apply the ratio test to n over 2 to the n. The ratio test says that rho, that Greek letter r, is equal to the limit as n goes to infinity of the absolute value of the ratio of the n plus first term of the sequence divided by the nth term of the sequence. The r here stands for ratio test. My n plus first term in this sequence is going to be n plus 1 divided by 2 to the n plus 1. Because n plus 1 is going to be strictly positive, as is 2 to the n plus 1, I will not need to include the absolute values, though it's not wrong if I do. The nth term would be n over 2 to the n. Now I have a complex fraction, so I need to perform some algebraic steps in order to simplify it. Pull it apart by dividing the numerator fraction by the reciprocal, or the denominator fraction, which means multiplying by the reciprocal. This gives me 2 to the n over n. n plus 1 divided by n does not reduce. The n plus 1 is a group. Either the whole thing goes or none of it goes. However, I can think of 2 to the n plus 1 as 2 times 2 to the n. That will let me cancel the common factor of 2 to the n in the numerator and the denominator. This leads then to the limit as n approaches infinity of n plus 1, the group, divided by n with a 2 out front. Now the 2 is a constant which could be pulled outside of the limit. This, of course, is another indeterminate form of infinity divided by infinity. This time, for fun, let's just go ahead and do L'Hopital's rule again. This would lead to, on the next set, the limit as n goes to infinity of 1 over 2. This gives me the value of 1/2. Because 1/2 is less than 1, I know that the original series does converge, but I have no idea what the sum would be. It is not a half, it is not related to a half. The 1/2 simply tells me that it does have a finite infinite sum. Let's look at another example. In example 3, we have the infinite series from n equals 0 to infinity of n plus 4 quantity factorial divided by the quantity 4 factorial times n factorial times 4 to the nth power. The exclamation point represents the factorial. Just to remind you of what a factorial is, remember that a factorial by definition for n factorial is n times n minus 1 times n minus 2 all the way down to 3 times 2 times 1. In other words, if I had 4 factorial, this would be 4 times 3 times 2 times 1. As a class of functions, factorials grow faster than almost every other type of function, with the one exception of tower functions. N to the nth power grows faster than a factorial, but factorials far outgrow exponentials and other algebraic functions. Whenever you see an exclamation point inside the sum end, it generally means you're going to have to use the ratio test. You cannot integrate with a factorial because they are always discrete functions, and you cannot convert them into something that can be integrated, which means that one of the only tests we have when we have a factorial involved is the ratio test. They're actually kind of fun, so let's do this one now. Before we get started, though, we need to decide, does the limit of this go towards 0 or not? In other words, the divergence test. In this case, if we compare the relative sizes of these here, the difference between the n factorial and the n plus 4 factorial are 3 additional terms. We'll see that provided that we choose a large enough n, the sequence will go down to 0. Let's simplify it a little bit and take an examination of the sequence. We're applying the divergence test to the sequence that is the summand of the infinite series. I've rewritten the n plus 4 factorial in its respective parts, but it looks like I forgot one, so let's add it in. It should be n plus 4 times n plus 3 times n plus 2, and I'm missing, times n plus 1, and then times n factorial. In the denominator, I rewrote the 4 factorial as 4 times 3 times 2 times 1. I left the n factorial since it's going to cancel with the 1 out of the numerator, and I left the 4 to the nth as well. Rewriting this now, I have the limit as n goes to infinity of n plus 4 times n plus 3 times n plus 2 times n plus 1, all divided by 4 times 3 times 2, which is 24, times 4 to the nth power. The 1 over 24 could be brought outside the limit. I know if I were to multiply out the 4 binomials in the numerator, I would have a 4th degree polynomial. However, in the denominator, I have an exponential 4 to the n. That means that if I apply L'Hopital's rule 4 times in a row, I will eventually find that the exponential has an order of magnitude larger than any polynomial, and it will outgrow it. This will drive the entire limit down to 0. This means that again, the divergence test failed. It's inconclusive, meaning it cannot tell me whether or not it diverges. The next step is to apply the ratio test. The presence of the exclamation point, which means that we have here a factorial, pretty much screams ratio test. Let's apply the ratio test on the summand. To apply the ratio test, sorry about that, hang on a second. Scrolling back down, there we go. To apply the ratio test, I need to find rho. Rho is the limit as n goes to infinity of the ratio of a sub n plus 1 to a sub n. Because my limit starts at 0, every factor inside the summand is going to be strictly positive. That means the absolute values are not strictly necessary, but it's not wrong to include them. It can be a little confusing to substitute n plus 1 in place of n when I already have n plus 4. I recommend that you go ahead and take an extra step and write it out without doing it in your head, just to make sure you don't make a mistake. It's very easy to make mistakes in these kinds of problems, but if you write them out the long way, they can actually be relatively simple. In this case, this entire numerator, the fraction, represents a sub n plus 1. Now let's rewrite it in the a sub n form, which is what it appears in the original summand. N plus 4 factorial divided by 4 factorial n factorial times 4 to the nth power. Notice that the primary division bar between a sub n plus 1 and a sub n is longer by far than the others. This helps me keep track of where the different parts are in the fraction. Now I'm going to do some algebra and divide by the denominator fraction by multiplying by its reciprocal. This leads me to the next step, which is that rho is going to be equal to the limit as n goes to infinity of, well, n plus 1 plus 4 would be n plus 5 factorial divided by 4 factorial times n plus 1 factorial times 4 to the n plus 1 times, now I take the denominator fractions reciprocal and multiply by it. 4 factorial, n factorial, 4 to the n divided by n plus 4 quantity factorial. In order to reduce here, I need to back it down to n plus 4. That means rewriting the numerator factorial as n plus 5 times n plus 4 factorial. In the denominator, I can rewrite the n plus 1 factorial to cancel with this n factorial by rewriting that as n plus 1 times n factorial. The 4 factorials will already cancel from this step here, and I can leave those out. This would give me n plus 1 in parentheses times n factorial. These two factors represent n plus 1 factorial, then times 4 times 4 to the n. Note that I pulled the extra 4 away from the power. This is still 1 plus n, 4 to the n plus 1, times n factorial times 4 to the n divided by n plus 4 quantity factorial. Now I've got more things that are alike that I can cancel. The n plus 4 quantity factorials cancel, the n factorials cancel, the 4 to the n's cancel. Let's see what's left now. At this point, all I have left in my limit, which I'll leave in black to distinguish it from the line above, is n plus 5 in the numerator, a 4 by itself, and an n plus 1 group in the denominator. The 4 is a constant which could be brought outside the limit if I wanted to. This would lead to 1/4 the limit as n goes to infinity of n plus 5 divided by n plus 1. I know that I can invoke L'Hopital's rule since I have infinity over infinity, and the derivative of each would give me 1. I can also play the Bill Gates rule and say this is just 1 over 1, leading coefficient over leading coefficient. Or I could do the algebraic method, which is multiplied by 1 over n over 1 over n. But frankly, that last method is a lot of work and a real pain. So I tend to avoid that one. In this case, I'm simply going to apply L'Hopital's rule in my head or the Bill Gates rule, which says when the leading degrees have the same degree, the ratio of their leading coefficients is the value of the limit. This leads to a value of 1/4. Because 1/4 is less than 1, I know that it must be a convergent series. It does not mean it converges to 1/4. That simply tells me that it does converge. When we have a series for which the ratio test is a good choice that are alternating in behavior, I can use the ratio test by taking the absolute value of the summand. This will allow me to determine whether it converges absolutely or conditionally, or whether it diverges or diverges absolutely. This is similar to what we learned in the previous section 5.5 in the alternating series test. This concludes this video on the ratio test. The next video will be about the root test, which is also out of section 5.6, which is used less often and is slightly shorter.